Okay, now there are again 5 topics. This is the first one from BIB. This is India's golden sweep at the 56th International Physics Olympiad 2026 held in Colombia. Now, International Physics Olympiad, okay, so there are 3-4 Olympiads like this: International Physics Olympiad, Chemistry Olympiad, Mathematics Olympiad, and Astronomy Olympiad. Okay, so this is the first time we have done a clean sweep, that is 5 on 5. Okay, now, so 5 students participated from India, all 5 of them won gold. Now here India secured the world number 1 rank jointly. Okay, so actually the way it is marked, that like number of questions you have solved and all that, so because of that many countries get the same number of marks, and that is why many countries top. So India is one among the topper. Now see this, with this exceptional performance, India secured world number 1 rank jointly with China, Kazakhstan, Russia, South Korea, Taiwan, all these. Okay, now what you need to remember here is, first is this India's performance in India International Physics Olympiad, and the other thing is remembering this institution. Okay, so this is the name of the institution, Homi Bhabha Center for Science and Education, a national center at the TIFR, Tata Institute of Fundamental Research. This is the institution where what happens, all these students which are like very meritorious and basically these are 11th 12th kind of students, so who are doing very good in all other regional mathematics olympiad, regional physics olympiad, so all of them are called here. They live in this center for some time, okay, and it's a fully residential program, and for a few months they train them specifically for olympiads, then they go and represent India. Okay, and this has performed very well till now. So just this name of this institution, and India has won India's performance in International Physics Olympiad. That is it. Otherwise, name of this people, that people, he credited this, who credited this, does not matter. Now, the other topic that we have is breakthrough in tritiated water filtration. Now, understand this, we have to understand a little. See, you know hydrogen, it has 2 isotopes. Know their names? Hydrogen isotopes. There is something known as deuterium and something known as tritium. Okay, so basically these are isotopes of hydrogen. Isotopes means atomic number is same, atomic mass is different, so they have an extra of neutron. Now this is deuterium and tritium. Now hydrogen forms a very important compound called H2. This, you know, this is water. Now sometimes what happens, because of some radioactive waste from nuclear plants and all, this H, one of these H may be replaced by this tritium, so it may form something like THO. Correct? Now the problem is that because it is almost very similar to hydrogen, so it can start replacing it in water. So when radioactive waste are released in the water, correct, from the nuclear power plants, what will happen? Some of those tritium can start forming compound like this. Now this actually behaves very similar to water. So using normal test also you won't be able to identify, because this is chemically very similar. But the problem is that this actually leads to beta radiations. So basically this is radioactive in that sense. So it can release some radiations which can cause harm in the long term. Understood what is happening? What is the issue? Now recently they have developed a system using metal organic frameworks which can prevent this, or which can clear this THO to normal water. We'll understand what is MOFs also. Now let's start. A new study has shown an efficient method to filter tritiated water. Tritiated water contains radioactive tritium. Then it is relevant to Japan's Fukushima Daiichi wastewater problem. So what has started happening? Japan has been releasing treated water into the Pacific since 2023. So what happens? They treat the water, then they release it in Pacific, but because there is also radioactive parts, small parts of tritium and everything available, so inside the water it is actually replacing the hydrogen, and that is a problem. Okay, so what is happening? this THO compound is being released and very difficult to filter out at the plant level because you cannot really identify it easily. Now, why it is difficult to remove? Because it is a radioactive isotope of hydrogen. Then it forms HTO. Okay, when it bonds with oxygen, then HTO behaves almost like normal water. So normal treatment system cannot easily separate it. Tritium is a beta emitter. All this we have seen. Then its physical half-life is about 12.3 years. So it will, whatever, because of radioactivity, it will become half by 12.3 years. Okay, then how does the new study work? This is the next thing that we need to understand. See, this is called metal organic frameworks. Now, metal organic framework is also something that got Nobel Prize in 2026. Nobel Prize in Chemistry. Okay, now what is this? This you understand. So basically, metal organic framework. Okay, if you just see these three words, it has a structure like this, where the dots, the nodes that you see, these are made up of metals. This connections, okay, this is made up of organic polymers. Now, how it is useful, understand that. So, what you might have seen. Have you seen those foldable stools or jack of a car? So foldable stool you might have seen, where there are connections, but there are nut bolts at some ends, and then there is metal in the middle that you can shrink or open like this, correct? Now, same thing you can do with metal organic frameworks also, based on what size you need it for. So let's say there is some heavy metal, some heavy isotope, like in this case. If I want to separate it, I will do what? I will take this framework and I will move it close enough so that the space is just large enough to catch this, and let the hydrogen go, because this will be slightly bigger, correct? So sort of like you have sieves now, for we use it in home, like for cooking and all, we use sieving. So similar is this, but of course, because these are atoms, and so you cannot use the normal sieve like a physical separation, so you use this. It provides a much larger surface area, and what happens, tritium will get clinged here, and that way it can be separated, and then hydrogen will be added back, so it will become normal water. This is metal organic framework, got Nobel Prize in 2026. This is one of the applications of this. It is also used in many other ways. Now see, scientists coated stainless steel mesh with something, okay. This MOF has many tiny pores and a very large surface area, correct? As tritiated water passes through it, the MOF removes tritium. It replaces tritium with normal hydrogen, making separation much more efficient. Understood? That's it. What is the significance? So it can improve nuclear wastewater management. Yes, it may reduce the need to discharge tritiated water into the ocean, correct? Why? Because it can take away those tritiums. Then it can make nuclear energy cleaner and safer. Then MOFs were awarded Nobel Prize in Chemistry in 2026 for their wide-ranging applications, including gas storage, carbon capture, catalysis, and water purification. Okay, so this was one of the applications. Other applications of metal organic frameworks is also given, like gas storage, carbon capture. Same way, basically how large is the spaces, based on that you can capture things. This is metal organic frameworks. Then next White Rabbit Technology Demonstration Network. Now see this. India's first Ethernet-based IST distribution network has been established, inaugurated at RRSL, Bengaluru. Now, it distributes Indian Standard Time over fiber network at sub-nanosecond precision. Now, first understand what is all this. See, first understand about little bit about its history. You know about this institution, CERN? What is this? Center for Nuclear Research in the European agency. Okay, so its name is some written in some European or French. That's why it is CERN. It is basically Center for Nuclear Research. Now, CERN is the entity which is very famous for developing many new things in fundamental physics. Okay, you might have heard of Large Hadron Collider or God particle. Okay, so those were also created here. Now, CERN has also, because CERN has to coordinate many machines at precise controls. That is, one machine operates, then the other, all has to happen within a nanosecond, because you are dealing with, say, Large Hadron Collider, for example, they are colliding two different protons or some kind of different subatomic entities. Now, for that, time precision is very important. So, in the process, they developed a mechanism, okay, which they called as white rabbit, which provides you much more accurate time signals. So, from GPS also we are getting time signals. We will study about GPS when we do science and tech lectures. So, what is happening? All these satellites, they are constantly sending signals. Okay, now based on your phone is actually a receiver. So, it receives signals from 3-4 satellites, and based on that it calculates where are you located exactly, the point, as well as the time signals that your phone needs. Now, this is much more precise than GPS. This is based on something that they developed. Now, White Rabbit, now why it is called White Rabbit? So, White Rabbit was a character in, I think, one of the comic books. So, where this character used to keep a clock with him. So, he was very precise with respect to time. So, he always used to have a clock and will always measure clock, all that he used to do. That's why they named it White Rabbit. It's nothing related to rabbit. Then, now, because it was so important, so they kept it open source, the hardware as well as protocol technology. Then, the White Rabbit collaboration was also made to promote, maintain and support its wider adoption, so that more countries can start using it. It is membership based collaboration that sustains this ecosystem. Now, how does it work? So, at India level, what is happening? So, all these, there are different entities from which you will be getting Indian Standard Time using atomic clocks. Okay, atomic clocks, you know? No, atomic clocks, see. Might have heard of rubidium, cesium, all that. There are some elements like this. Now, what is special about those elements is that they complete, like one electron going from this level to this level and then coming back. This is the motion it is performing. Now, it has been found that, for example, let's say for cesium, some random figure, these many cycles of this movement is completed in 1 second. They have found this as the fundamental property in a cesium atom. Now, if this is known, now you can understand that this will make the calculation of 1 second very accurate. Why? Because they are counting number of cycles. So, if the number of cycle came out to be even this, then they know that there is an error of very small margin, but there is an error. So, if they are able to ensure that the number of cycles is this much, you get exact 1 second. And this is called an atomic clock. Why it cannot falter usually? Because this is based on fundamental property of that atom. We are not doing anything. We have just observed that something like this happens. And we are just observing it constantly, and usually they tend to remember constant. This is a way of measuring time. So, this is atomic clocks. So, first is those old methods of getting time from the atomic clocks itself. Now, this IST is sent through Ethernet or fiber using this precision time protocol. Then WR measures delay and automatically corrects clock drift. Now even after this is what on which GPS or India's Navik, all this are based on atomic clocks. Now once this data is captured, to make it more accurate, then we will be using white rabbit technology to make the time control even more accurate. This is what has been done. The result is all connected devices stay synchronized to less than 1 nanosecond. Then why is it important? So first thing is reduces dependence on foreign GPS timings, then protects critical systems from timing errors, spoofing. Okay, supports defense, power, banking, stock exchange, 5G, 6G, quantum communication and space missions. Everywhere, see, time signals, accurate time signals are important in almost every domain that you know of. From banking to power to quantum tech to supercomputing, everything that you can think of, if I can give you more precise time, it will become more efficient. As simple as that. So this can be used here. Now, protein biosensors. See, protein biosensors. Biosensors are what? Biosensors are what? Something biological they must be using to sense something in you. That much you can understand. This is a biosensor. Now, earlier biosensors used to be made from antibodies. Now, how they used to work? Understand first that, then we'll understand the newer mechanism. That is, there are two mechanisms, antibodies and aptamers. Okay, now see. Let's say I want to identify a particular disease, that this person, let's say, has sepsis or not. Now what I can do is basically I take let's say a strip and I pluck a dot on his finger, and from that I collect the blood sample and I check it using a strip, that does he have sepsis or not. Now what is happening here, these strips or something like similar devices are here from a very long time. Now how do they work, that you understand. So there is antibody. So what they do, they first take small sample of that same disease. Okay, so same disease, same pathogen, they will take and they will inject this. They will inject this in, for example, a rabbit or rat, etc. All these animals. Now what will happen? Their body will start producing antibodies against it. Correct? Small amount of antibodies. Now these will be extracted out of them. So antibodies that are generated here, antibodies, these are extracted out. Now once they are extracted out, then they are used to make the strip or used in the machine, that is used as a biosensor. Now what I will do, I will take, let's say, your blood sample. Now if your blood sample has the same pathogen or the same disease, what will happen? Now you have the pathogen. Here what you have on the machine or strip, you have the antibody. So they will immediately cling to each other. Once they cling, that sends a signal to the machine that this person may be having a higher concentration of this pathogen, so probably he has this disease. This is the old method of how diseases were detected. But don't you think this is a very long process and also little difficult, because you have to get an animal, then produce antibodies, then extract it out of him purely, then make those strips, all those, this is very difficult, correct? Very long drawn process. Also it may not be exactly accurate. Okay, now the modern one is much better than this, understand that. So this is protein biosensors, devices that detect specific target proteins in blood or body fluids. They have two main parts. See, recognition element, as I explained you, this binds to the target proteins. So in that case, it used to be antibodies. Those were used to target those proteins so that it binds to it. Now, signal transducer, what this will do? This will convert this binding into a measurable signal. So how strongly they bond, this transducer will tell that what is the amount of this disease progression in this person. Understood? So two elements, one is to lock it, other to send the signals that this has been locked. Now, why in use? So new platforms allow real-time bedside detection of multiple proteins, replacing slow lab tests. Now, this is what we have to understand. So this is why it was in use. How has the recognition element evolved? Now, I will just explain you, this is fine. Antibodies, you understood how we were using it. Now, instead of antibodies, because right now we have moved much forward in genetic engineering. So basically, instead of getting those antibodies from the animals, this, that, just by seeing the pathogens, we do understand what might be the structure that may cling to it, or what might be able to recognize those pathogens. So that we make in lab itself. So this will be some strand of DNA or RNA that we completely make in labs. Now those will be in the sensors. Now, because those things can be mass produced in the labs or in factories, correct? So that makes the biosensors much cheaper also, because I can keep on testing that what segment of DNA can catch it much better. So over time it will evolve much better, correct? And it will be more precise also. Okay. Then one more thing, the natural antibodies that you took out from that animal are usually very unstable. Okay, like the eggs you have now, if you heat the eggs a lot, they will just break. They won't be able to survive. Similarly, antibodies also, when you take it out, you have to refrigerate it, you have to keep it cool in proper environment, otherwise they go defunct. But these are made in such a way that they are much more stable. So these modern sensors, that's why, can be used anywhere. Okay, now you see the difference. Origin is natural, this is synthetic. Then production, expensive and slow, cheap and fast. Stability, heat sensitive, this one. Antibodies, this is highly stable. Last, scope, limited targets. Now, can be custom built for almost any target. Correct? For some of the diseases, what happens? For example, tetanus. Now in tetanus, what happens? Even the very small quantity can cause the disease in you before you can even form antibodies. It is so toxic that before you can form antibodies, your body identifies it, you already have the disease. Okay, so now in those cases, you cannot have it from an organism and then get the antibodies. All that becomes difficult. So this can work for almost any target, and now it has evolved so much that using artificial intelligence, they have custom built such biosensors which can sense many diseases at once. So basically, they have your blood sample, let's say blood sample or some body fluid sample. From that, it can check for 4 or 5 diseases or many diseases in one go, because it has all those different DNA strands needed for that particular disease, and it is able to identify, give you immediately. And that is why it is being called that these are bedside biosensors. That means right then and there, you will get to know that what is the spread. Okay. Now, how are modern technologies improving biosensors? Now, all these are we learn in different chapters. One is nanotechnology. So this increases surface area for higher sensitivity. Then CRISPR-Cas9 we'll learn about. This is a cutting tool. Okay. So this is how you cut DNA segments, because you have to make those particular strands. Now, so this can be done by CRISPR. CRISPR-Cas9 as a whole is a molecular scissor. Okay. How you cut DNAs, how you cut paste here, there, all that. So CRISPR enables highly precise target detection. AI analyzes complex signals for instant diagnosis. Wearables enable continuous non-invasive monitoring. Okay. Then, what are the challenges and significance? Challenge: making biosensors affordable and scalable for Mass clinical use. Significance: enables faster diagnosis of diseases such as sepsis, heart attack, cancer. Supports point of care diagnostics, reducing dependence on central laboratories. You understand the difference? Central laboratories, basically I have to take the sample, then I have to send, then they will test in the lab, then lab reports will come. What is this? Point of care diagnostics means right then and there it will be able to diagnose that this person has this disease or not, or what should be the process going forward. Right now what I have seen in hospitals, what they do, they have these also point of care diagnostics. So they first test this, and after this, just to be very sure about it, they send it to labs also and then get the confirmation reports. But at least you can start the treatment right then and there because of this. Then this is the last topic. Now, you know about electromagnetic spectrum, EM waves you might have heard of, radio waves, microwaves, UV light, visible light, all these. Okay, so this is a spectrum like this. Now, what happens? For example, this is, let's say, X-ray, UV ray, then this is visible light, infrared, all this. Okay, so it goes on like this. Now, within visible light, now what happens from here to here, you understand intuitively what is happening to the energy of these particles. What do you think? Which has more energy? This is the correct order for energy. Energy is increasing constantly, correct? Like from visible light, your skin or nothing burns, correct? But if you look at UV light, you are in the UV light, it can penetrate in your skin and can cause issues. X-rays can go beyond your skin and even see what is inside you, your bones and all, correct? So basically the penetration power or the energy is increasing in this direction. Now, so energy is increasing in this direction. Now, E is equals to hc by lambda. Now, what is this? See, these two are constants, does not matter. What you have here is energy. If this is constant, can I write it like this? Energy is inversely proportional to lambda is actually wavelength. Now, you know what is wavelength? Wavelength is what? What is wave? Yeah, so basically, if there is a wave like this, then you start from this point. When you come back at this point, exactly on the same level, you went and came back like this, this distance is called wavelength. Now, for us at this level, wavelength is directly proportional to just size. That is, if something, for example, if this wave is elongated like this, then it will have longer wavelength and it will also have larger size. Correct? So, longer wavelength, larger size, smaller wavelength, smaller size. Correct? So, for us this much is enough. Energy is inversely proportional to size of the particles. Now, if you understand all this, now in visible you have here infrared, you have here ultraviolet. How should I write VIBGYOR if I want to write in the energy diagram? So here you have ultraviolet, so violet must be very close to it, correct? Here you have infrared, so red must be very close to it. You might have heard of VIBGYOR, correct? These are the 7 colors, the rainbow and all that, okay? Now, so this is VIBGYOR. Here you have violet, here you have red. Now, energy diagram you have understood, wavelength is exactly opposite. So, wavelength actually increases in this direction. Why? Because they are inversely proportional. That means which will have higher wavelength between violet and red? Red will have higher wavelength, correct? So, that means red is higher wavelength or size. Clear till here? Now, if red has higher wavelength or size, what happens? For example, if two people are trying to pass, let's say I am trying to pass and a child is also trying to pass. Now, if there is some small grasses or something like this, now for whom it will be a bigger obstruction? For him, correct? Because he is small in size, I'm much bigger in size, I might just step over it and move forward. That is why what happens, the particles which are large, they are not obstructed by small things like dust particles, some small molecule here, there, they are able to penetrate it. It's like an elephant walking. Have you seen elephant walking like this? No. Elephant walks straight. Why? Anything does not matter to him. While the deer walks like this all the time. Correct? Because nothing is an obstruction for the elephant. Now, because the red is much higher in size, it is not obstructed by all these things. That's why it can go straight or basically go along the same line for longer distances. While blue light is something which is smaller in wavelength, blue means very close to this, smaller in wavelength, so that will get scattered a lot. That is why when I have to send signals, for example, the ambulance, okay, or any kind of signals are usually red. Why? Because red can travel straight from one direction to the other without any obstruction or without changing its direction. That's why red lights are used in the signals. Why? And this also explains. From this, can you explain me why sky is blue and why during the sunset and sunrise sky looks somewhat red in some regions? Why is the sky blue? Which light? Blue light, correct. So basically this is again coming from the scattering principle, because blue light, smaller wavelength, gets scattered a lot. That's why when sunlight has all the 7 colors, it is white light, it is coming towards it, blue light is scattered all around in the sky and the sky starts looking blue to us, correct. Then why during the sunrise and sunset we can see red? Yes, so yeah. So basically what happens when sun is just about to set, basically if this is earth, now here you have the sun or here you have the sun, correct. So now what happens, this light that is coming from the sun towards our location, wherever you are located, let's say in Bangalore, is reducing. So the intensity of light has reduced so much that only the red light is able to travel and reach you. The intensity of light is so low now that the blue light, whatever was there, it will be just scattered somewhere here and you can't even see it. Here, because when it is right at top of you in Bangalore, the intensity is so high that you can see all the colors. And that's why, because blue is scattered, so you see blue sky. But when it is almost about to set, after a point you don't see the sun. Nah? So this is that time, sunrise or sunset. So only red light is reaching you. Because of its higher wavelength, it is not scattered by anything and reaches you. That's why it looks red. This part will look red, other part is almost getting dark. Then, so red has the longest wavelength in the visible spectrum. Longer wavelengths are scattered the least in the atmosphere. So red remains visible through fog, dust, rain, all of this. Hence it is used for danger signals, signs, traffic lights, warnings, all of these. Then what is the science behind it? So this is all that scattering that I explained you, white light going into 7 colors. This is called Rayleigh scattering. Causes shorter wavelengths to scatter more. Then hence blue scatters the most while red scatters the least. The same principle explains blue skies and red sunsets. Now, Now, why do humans associate red with danger? So this is also evolutionary. So red is the color of blood and fire. It can trigger a mild fight or flight response. It attracts attention faster than most other colors. Again, same reason. Red also contrasts strongly with natural backgrounds like green vegetation and blue sky. Because Earth, if you might have seen those solar system, might have seen Earth looks blue and green, correct? Now that is why red contrasts much better. If I were to use something on the Mars, now Mars is mostly red colored planet because of Fe2O3, okay, an iron compound. It looks reddish. Now there I won't be using red color because everything is red, correct? So even though it might be scattered less, but everything is anyway red, so it will not create that contrast, correct? And that is why we use red color. Now what is this Mars connection? So Mars appears reddish due to iron oxide. A red bonding sign would blend with the Martian background. Then deep blue, the complementary colors of red would be a better contrast on Mars. Can you tell me one thing? You might have seen animals. Animals are mostly like green colored or something they have, correct? So that they can hide well in the jungle, correct? Either they are very brownish, okay, so that they can hide with the soil, or very greenish, correct? Why some animals like tiger is orange in color? Is it good for him? The deers can see it very clearly, na? In the vegetation, it looks so beautiful, vibrant. Huh? Why evolution made him orange? To make his life difficult or to save the deers? What is the reason? By evolution, it should have become green, correct? So as to hide in the vegetation and then attack on the deer. Why it looks orange? It's a predator, yes. It has its own skill. So he's backing his skills. Huh? No, the thing is, the colors that you understand is because human eyes has three cones, that is blue, green and red. Okay, now deers do not have red cones, so for him he appears green, so they can't see it. We can see it because we see red also. Okay, so for him he is doing camouflage only. They can't see it and then he attacks them directly. Okay, now let's do questions. Try this. Options are like only one correct, only two correct, only three correct, none correct, all three correct, none correct. What do you think? Options are only one, only two, like this. All three, none. What do you think? Only one? Okay. Let's see. First, standard water treatment systems easily separate tritiated water because its chemical behavior is vastly different from normal water? No. If this was so, then we won't have this technology, MOF, all that. Then, tritium is a radioactive isotope of hydrogen that decays by emitting alpha particles. Alpha is not even possible. Alpha is like helium 2 plus, not even possible. Then, next, metal organic frameworks can filter tritiated water by replacing tritium with normal hydrogen. Yes, only one becomes the answer. Do this. White Rabbit technology, proprietary hardware protocol developed exclusively by ISRO for space synchronization? No, CERN developed it. Then it completely relies on foreign GPS timing to synchronize domestic network? No, correct. This is what we want to get rid of. That is completely relying on GPS. So first we developed Navik so that we have our own atomic clock wala system, and the other thing, now we are making it more precise using White Rabbit. White Rabbit is not like something that European Union controls. It's an open source, correct? So we have integrated it, we are now part of it. So this is how we are trying to bypass the GPS. Then it distributes IST over fiber networks with sub-nanosecond precision. Yes. So this and this is wrong, this is correct. Answer only one. Then consider the following statements about protein biosensors. Try this. What do you think? Correct. So basically, first one, apetamers are natural recognition elements harvested from animals' immune system? No, that was antibodies method. Traditional antibody based on sensors are highly stable? No, they are unstable. Then modern biosensors use CRISPR technology to enable high precision target detection? Yes. Okay, if it was necessarily use CRISPR technology, then it will be also wrong. Okay, this is a general statement. Use CRISPR technology. So don't take it like they are saying that it must use. If they have to say must use, they will write necessarily, essential, then only mark it wrong. Otherwise, treat this as a general statement. Then last. Think about it. You can get to it. Scattering intensity will be something involving scattering. Which gets scattered more? Like that you think. What do you think? One only. What do you think? Huh? Which one is correct? Only one. Okay. Now let's see. First, red light scatters the least in atmosphere because it has longest wavelength in the visual spectrum. Absolutely correct. Then last, a red warning sign would provide the best visual contrast against the Martian landscape. No. Correct. There, the complement of red, something like blue, will work better. Then this, according to Rayleigh scattering, scattering intensity is directly proportional to fourth power of wavelength. Now, you may not know fourth power this that, but you at least understand that scattering intensity means more scattering. Correct. Which light goes through more scattering? Blue light goes more scattering. Correct. So that means if I put the wavelength of blue light, then the scattering should be more. That means what? That means blue light has more wavelength or less wavelength? Less wavelength implies more scattering. Now what do you think? Aren't they inverse in relation? Less wavelength, more scattering. So that means scattering is inversely proportional to wavelength. Some power, I don't know the power. It may be 3, 4, whatever, but I do understand that it does not increase with wavelength. Correct? That much only we need to understand. It says scattering intensity is directly proportional to fourth power of wavelength. No, it is inversely proportional to fourth power. Okay, so this becomes wrong. Answer becomes only 1. Okay, that's it. Thank you.